Welcome back. So this is part 2 of solving higher order derivative differential equations using system of differential equations. So we learned from last lecture that we can convert a higher order derivative to a system. We looked at the pendulum problem. We solved this using spreadsheet. So this is the result of it. I was explaining that you can actually look at the result. After we solve, this is y against time. This is basically you can think of the angle of the pendulum against time, right? And we see that the angle goes up and down, and then this peak actually is going down and down and down, which is a bit weird. But that could be because of the zeta. So zeta can be interpreted as maybe the friction or something like that. So if the friction is 0, then the magnitude of the oscillation should not change. If we increase the friction of the pendulum with air, then the pendulum is going to stop quicker, right, or faster. So you can see that as you increase zeta, what happens, and that's what we have in the spreadsheet here. If you go to the Blackboard example 5.6, there's a second tab for this problem, and in this tab actually I look at other different zeta values. So you can basically redo this whole thing with different xi or zeta. I actually rename it to xi, but it could be zeta. I have it zeta here, but that's the same as xi. Okay, so these two columns are the result for y and z when zeta is 0.5. This is when zeta is 2, and this is when zeta is 0.1. And then here I plotted y against time for zeta. This is zeta 0.1, low zeta, and then we go to higher and higher. So as you increase the zeta, you see the oscillation actually becomes weaker and weaker. Basically, it doesn't oscillate anymore if the zeta is too large. Okay, so no oscillations. It goes to the solution, to the equilibrium solution at the end. And if the zetas are small, it's going to oscillate up and down, but at the end reaches to that condition. This is the comparison including the z values for two zeta values. So when zeta is below 0.5, we can look at y and z. Remember, z was the derivative of y. Again, here, z is the derivative of y, right? So now we can look at, let's say, blue is the derivative, right? So that's z, and then the corresponding y would be this one, right? So this is y against time. It's a little bit of oscillations because zeta is low, and then this is the derivative of it, which is z. Now if you go to high zeta value, which is the green for y, and the corresponding z value would be the red. Okay, so you can think of z is the derivative of y, right? If the y is the angle of the pendulum, then z is going to be derivative of that, which means the rate of change of angle, which means the velocity, sort of. So this tells you that the velocity goes up initially and then goes to 0. It's going to stop if the friction is high, which is zeta. And if the friction is low, the velocity goes up and down, like plus minus, because it goes back and forth, and then at the end it's going to stop. So no friction, more oscillations, high friction, few oscillations, or maybe no oscillations. Okay, so that was example 5.6. Now in the next example, we're going to look at how we can basically do this using VBA, because if you really want to drag down this for like 1,000 rows or so with different details, that's a little bit more involved. You have to change these cells manually, and we don't want to do that. We want to have a spreadsheet that can easily solve the system without having us interact with the system. Okay, so this would be example 5.7 of the textbook, which is the automated version of solving linear system using VBA. Well, the text actually talks about Euler method. We can think about the Euler method, but we can actually extend this to any other method like backward Euler or ch205 trapezoidal method. And in this video, I'm going to cover how we can do the pendulum problem using VBA and forward Euler. Okay, so that's example 5.7. So here is the VBA script for that, and here's a spreadsheet. So let's see how we can do this. All right, so if you remember from chapter 2, we want to solve the system using VBA. So first we're going to read out the variables from the spreadsheet. The variables we have is the number of unknowns. For now we have two unknowns, y and z, that we have to solve for. And then we need to know the h, the increment in time, let's say that's 0.1. We need to know the maximum time, how far I have to go. So this is the maximum time, 0.5, let's say. And, I'm sorry, 10. And then we need to know the zeta. Okay, so these are four parameters we need to know: zeta, maximum time, increment, and the number of unknowns. Then we want to create a table like time, y, and z, and be able to solve y and z for every time value. So here's the macro. So first, we put the base. That means the index of any variable should start from 1. We need to explicitly define the variables, which one is double, which one is real, which one is integer, which one is not integer. We have to set all of them here. So I'm going to have two variables, one for y, one for f. Okay. So these would be double. I need one for increment. I need the intermediate time variable. I need the maximum time counter. I try to have explanation in front. I need the acting row. I need some loop counters. The maximum number of iterations that I want to have. Oh, sorry, the maximum number of variables we're going to have, which is n right here too, and then the zeta. All right. So let me just make sure that we have z variable as well. Right. Okay, so this y is actually a vector, and vector of size n, and n is 2, right? We have only two variables. So both y and z in the spreadsheet actually are hidden in the y variable. Y is an array. Okay. Okay. So we're going to activate the sheet. We're going to clear this up. So first we're going to define a variable called last row. Every time you run the code, you want to clear the previous run and basically overwrite the new result on top of it. Okay, then we define last row, which is going to be, we're going to look at a box that starts from column A. It gets column A, go to the last row of column A. So this actually finds the last row. This finds the last row of column A. If there's any text or number in column A, it's going to go all the way down and find the last row of it. So the last row now gets attached to the block. Next, we're going to have a block of A4 and column C. So A4 is this cell. We're going to say from A4 to column C, and how far we have to go down to clear the previous simulation result or previous result in the spreadsheet. Okay, this gets the range of cell A4 up to C column, and then that's the so from here to here is the column, the number of columns we're going to get, and then how many rows we have to go down. That's actually with the last row that we found before in the previous line. And then we're going to apply clear, so we're going to clear all these cells within this box all the way to the last row. All right, then you're going to get the number of unknowns from the active sheet, which is sitting on cell 1, right here. So that is the number of unknowns 2. You're going to redimensionalize our y vector and f vector to contain only two variables, because we have only y and z, right? Y and z. You're going to get h, maximum time, and the current time value from the spreadsheet. The h is going to be right here, which is row 1, column 3. You're going to get time max, which is in row 1, column 5, right? That's time max. And then we also get zeta, which is in row 1, column 7, and that's zeta, right? Then we're going to have a loop. We're going to read the initial condition. So these three are just to get the initial condition. and those are sitting in row 3. So that's why I have row 3, and then we're going to have to go from column 2 to column 4, because n is 2. From column 2 to column 4, that means this and this. We're going to go over these 2 cells and then read the initial condition. Then we're going to start from row 4 and then try to calculate the rest of it. So for every row, we have to do the forward Euler, and that's why we call this function fcalc1. So fcalc1 is nothing but the right side of our equation, right? The right side of our equation, if you look at the pendulum problem right-hand side, okay, the right-hand side of the first equation is z, but the z is the second component of our y vector. So that's why we have here the first element of f, which is the right-hand side of our differential equation, is the second element of y, which is z. That's why equal to y2. Now the second element of f, which is the right-hand side of the second equation right here, it's 1 minus 2c and then z minus y. And that's what we have here. 1 minus 2 times c, this is z, which is the second element of y, and minus y, which is the first element of y. So by the way, the y we have here is a vector. It's different from this y. This y has 2 elements, y1 and y2. y1 is equal to this y, and then y2 is equal to this z. Hope this is not confusing. Okay, every time you call f1 or fcalc1, it's going to calculate the right-hand side of the differential equations for us. Then the rest is very simple. We just do a forward Euler on every component. So we go over 2 elements here because we only have n equal 2. We have only 2 elements, y and z. For every element of y, we add the previous y value, okay, to h times the corresponding f. So this is, let's say, the new y is equal to old y, or yn plus 1 is equal to yn plus dt, or h times f of yn tn, right? And so because we have index I, it actually does that for corresponding element. So this calculates y and z both. Then we increment time by another h. Okay, for every interval, for every iteration, we have to increment our time. Then we're going to record it on a spreadsheet. We're going to put this time on the spreadsheet at the current acting row first column. So the time goes onto this column. Then we're going to print out the y and z, the 2 elements of y, right? We get the y value and then we store them into the value of the cell sitting at act row and column 3 and 4. I'm sorry, column 2 and 3, because I is 1 to 2, then the column would change from 2 to 3. So we're going to put the values into column 2 and 3, okay? So we're going to iterate over this loop. That means for every row, we print the t value, and then the y value, and then the z value. So the t value is printed here, y and z value are printed here. We iterate over the loop, so that means we're done with that row. We increase the act row, and then we iterate over the next row. And then the cycle ends when the maximum time when time reaches maximum time. At the end, we're going to change the font size to 12, so we're going to select the whole sheet. Okay, so this means we select the whole sheet, and we change its font size to 12, and then we're going to change the font name to Arial. Okay, this is just for beauty, nothing else. This is it. So you can change, let's say I'm going to change my zeta to 0.1 and run the code. So go in here and then go run, reset, run, and run. You see the solution changes, and here's the output. This is the solution of y against t, or time. I think in the bottom plot, there's no bottom plot, yes. So there are 2 more tabs here. In the next video, I'm going to cover how we can use this macro to solve 3-species system and maybe a 3rd order differential equation. So this pendulum problem was 2nd order. We can also look at another more complicated problem, which is 3rd order. All right. Also, there's another tab for 3 species. This species A, B, C we did before using forward Euler. Now we can see how we can solve that using this macro. The macro actually is very generic, and it's not very long, so I hope you can follow. Thanks so much. Stay tuned for the next video on VBA programming for solving differential equations.